Well, hello again. Imagine seeing you here. Today we are going to look at the fast, non-specific portion of the immune system, the innate immune response. Innate means inborn or natural, so the innate immune system is one that we have in place from birth. Sweet, here we go. The most basic of defenses against pathogens are the broad, non-specific barrier defenses. These barriers don't care who you are, they just care that you aren't supposed to be there. They block anything and everything foreign without discrimination that is trying to gain entry into the body. These barrier defenses work by preventing pathogen entry in the first place. After all, a germ can't make you sick if it can't get in. The skin is the primary barrier defense against the entry of microorganisms. The dead cells that make up the epithelium are too dry to be hospitable to bacterial growth, and the continual sloughing of epithelial cells disposes of anything that does stick. Sweat and other skin secretions also lower pH, further discouraging pathogen growth, and also physically wash the pathogens away. Saliva is another barrier defense. It contains an enzyme known as the lysozyme, which is a natural bacterial killer. Should it make it past saliva, the highly acidic stomach also serves to kill off offending invaders. Finally, mucus in the digestive, respiratory, and reproductive tracts, as well as in the eyes, ears, and nose, help trap pathogens, making them easier to clear and stopping their trek through the body. If you notice that many barrier defenses are concentrated around the digestive and respiratory systems, you are spot on. These areas are high risk for invasion due to their direct exposure to the external environment and pathogens on food and in the air. They're everywhere! Thank goodness for barrier defenses. The innate immune response system has special cells that help fight pathogens. Phagocytes are cells that surround and engulf another cell or particle and eat it in a process known as phagocytosis. Much like this classic video game character, they cruise around munching down on foreign material, debris, old cells, and pathogens. Yum! If it helps, phago means eating and cyte means cell. They are literally eating cells. Macrophages are a specific type of phagocyte. The most versatile phagocyte, it can move through tissues and capillaries with ease, and it's the first line of defense if the body's barrier defenses fail. They are always on duty. A neutrophil is another type of phagocyte. Unlike macrophages, they have granules, and rather than always being on guard, they only come to the body's defense if called upon. Infected tissues send out chemical signals through the bloodstream which cause the neutrophils into action. Monocytes are undifferentiated cells that can become a macrophage or a dendritic cell and circulate looking for areas of infection signaled by molecules of inflammation. Another type of cell for the innate immune response is the natural killer cell. Doesn't the name just sound ominous? Natural killer cell. We should all come with warnings for pathogens. Beware! Contains natural killer cells. NK cells can induce apoptosis in cells infected by bacteria and viruses. Apoptosis is programmed cell death and basically means they cause them to self-destruct. Cool! In response to chemical signals, natural killer cells can express the Fas ligand, which binds to the Fas molecule on an infected cell surface. This then causes the cell to induce its own apoptosis, killing both the host cell and the pathogen. Alternatively, the granules inside the NK cells can release perforin proteins and granzyme enzymes to destroy an infected cell. Perforins form pores and infected cell membranes through which protein-digesting granzymes enter and trigger apoptosis from the inside, like the drill pictured here, making holes and filling infected cells with killer enzymes. Yes! To summarize, Fas ligands initiate apoptosis from an infected cell's exterior, while perforins and granzymes initiate apoptosis from an infected cell's interior. And all this happens without us even knowing or thinking about it most of the time. I don't know about you, but I'm feeling pretty powerful. So just how do cells of the innate immune response know that a cell is infected? Enter the pattern recognition receptor. The pattern recognition receptor is on the surface of the cells of the innate immune response and recognizes characteristic features of pathogens as well as molecules that are stressed or damaged cells put off, kind of like recognizing fingerprints. However, these PRRs are fairly nonspecific and must identify a wide variety of pathogens with a limited number of receptors. This makes them less effective and targeted than other approaches. However, when a PRR finds a fingerprint, a pathogen that they do recognize, they will bind and initiate phagocytosis to eat the pathogen, even if it is outside a cell, or cellular apoptosis if the pathogen is already inside the cell. Inflammation is the hallmark of the innate immune response. It is triggered by damage to the cellular contents, regardless of a break in physical barriers like the skin. The inflammatory reaction itself brings phagocytes to the area to clear debris, kill pathogens, and set the stage for repair. The inflammatory response also attracts other cells of the innate immune system, as well as extra fluid to help clear the debris. Inflammation also helps isolate and seal off the site to limit pathogen mobility to other areas. It is important to note the difference between acute and chronic inflammation. Acute inflammation is a short-term response to injury. However, if unresolved, it can lead to chronic inflammation, which can lead to major tissue destruction and fibrosis. Chronic inflammation is ongoing and long-term and can be caused by foreign bodies, persistent infections, and autoimmune diseases. There are 4 key parts to the inflammatory response. First, an injured tissue releases mast cell granules and mediators of inflammation like histamines. Histamines cause local vasodilation or widening of the blood vessels to increase blood flow to the area. This vasodilation is the second part of the inflammatory response. Histamines also increase capillary permeability in the injured area to allow plasma to leak out and accumulate in the interstitial tissue. This is the third part of the response, and also what causes the characteristic swelling associated with the inflammatory process. Finally, leukotrienes released by the injured cells and innate immune cells in the area attract neutrophils by chemotaxis or chemical signaling. These macrophages clean up site debris and phagocytose pathogens. As they die, their remains become visible as pus. Pus. For the first 4 to 5 days, the innate immune system dominates and attempts to control pathogen growth. However, it usually does not stop pathogen growth completely, and the adaptive immune response will begin to increase and dominate to finish clearing the pathogen from the body. Speaking of pathogens, we will now take a closer look at the body's response to specific pathogens. The body has many different ways to fight pathogens, which is great because the more tools it has to fight, the more likely it will meet with success. Some bacteria, like Mycobacterium leprae, are resistant to the usual lysosomal enzymes that typically destroy bacteria. In these cases, the bacteria remain inside the macrophages, which then turn on special metabolic pathways like macrophage oxidative metabolism. This pathway produces nitric oxide as a byproduct, which can then kill that stubborn bacteria lurking in the macrophage. Bye-bye, bacteria. Sometimes the immune system can become depressed, which makes us more susceptible to opportunistic infections. They are called opportunistic because they take advantage of the opportunity to invade when the immune system is weak. Fungal infections, like those from Aspergillus, Candida, and Pneumocystis, are just such opportunistic infections. However, the traditional immune responses used to kill bacteria are often also effective on fungi due to their similar cell wall structures. So, we know how we can fight off bacteria and fungi, but what about parasites? Helminths like tapeworms and roundworms can be accidentally ingested through contaminated food and even from pet feces lurking in the environment. But look how cute he is! Surely he doesn't have worms. In the case of helminth invasion, eosinophils play a large role in defense. They arrive on the scene and release their granules upon arrival. Mast cells also degrade, increasing vascular permeability and making them more leaky. This extra fluid release can help flush out the parasite and its larvae from the body. Phew, parasite defeated. Want a free life lesson? Don't go barefoot in the yard, particularly in public places. Worms can actually be taken up through the skin in contaminated soil, like the helminths known as hookworms. Wear shoes! You're welcome. Finally, let's close with a look at how we defend ourselves against viruses. If they are located before they enter a cell, viruses can be effectively neutralized by antibodies. However, antibodies cannot penetrate the cell membrane, so if they make it inside a host cell before the antibodies find them, the antibodies are powerless. Wah, wah. NK, or natural killer cells, are great at recognizing and destroying cells that have already been penetrated and infected by a virus. Interferons can also slow the replication of viruses, but have a limited ability to eliminate it completely. Key to the viral defense system are the cytotoxic T cells. These cells gradually overwhelm the virus and kill off the infected cells before they can replicate. Brilliant! Well, that does it for lymphatic and immune system innate immunity. See you next time.